Now we move to our fifth paper. It will be presented by Markus Berchtold and is titled Fatigue Testing at 1 kilohertz Testing Frequency.
Thank you for the introduction. Welcome to my talk, in which I would like to highlight new possibilities in fatigue testing in the high cycle and very high cycle regime. My name is Markus Berchtold, as we heard, and I'm from the company Rummel. We are specialized in developing, manufacturing, and selling fatigue testing machines which work with the resonance principle with the electromagnetic drive. And 4 years ago, we could present the first prototype of a new testing machine with 1000 hertz testing frequency. And by now, it's a proven major design, I would say. And so we learned that we should test more than only 1 or 10 million cycles in some cases. And thanks to the availability of very fast testing equipment, which works with the ultrasonic principle on the resonance frequency of 20,000 kilohertz, a lot of research took place. But there is an old question of fatigue testing, which cannot be neglected. What is the effect of the loading frequency on fatigue life? And maybe also the size of the specimen is a concern, since inclusion are very important, especially for inhomogeneous material. The size of the specimen is a concern. So our machine, I think, can help to solve such questions. First, I want to describe quickly the machine and then talk about frequency effects a little bit. The testing machine is relatively small and compact. The weight is 1,200 kilograms. It has a capacity of 50 kilonewton statically and dynamically. So any load range can be tested. The loading frequency depends on the specimen stiffness, since the machine runs exactly in the resonance frequency. So depending on the specimen, the frequency is between about 980 and 1040 hertz. So we have also the advantage that if there's any change in the specimen, we see that in a change in a drop of the testing frequency. Yes. The dynamic displacement is limited to 0.1 millimeter, since we want to limit the acceleration to about 400 times gravity in peak load, not to exceed that limit. We have to develop a new controller for that because of the higher loading frequency. And finally, what is to mention, the sound is very terrible, so it's not nice to hear 1000 hertz tone. So sound insulation is very important. And even if the sound is below the required limits from the regulation, it's still very annoying after some time, so it needs to be put somewhere in the cellar, far away from the working people. The 1000 hertz frequency could be achieved with the vibration spring, with a very high stiffness and a small mass. Here the vibration head is the oscillating part, and the upper part, the cross head, and the fixture on the upper side is relatively quiet. Also, the static drive is in the bottom part with two spindles. A challenge is the correct measurement of the load in such a system, 1000 hertz, because of the high acceleration. So we have a 2 force measurement system in place, one for the dynamic force, which is in the upper part, which lets less vibration directly above the fixture between the crosshead and the fixture. And we have 2 normal Rummel strain gauge load cells at both columns to measure the static force. The piezoelectric system has the advantage of a small mass and a high reach and a high stiffness, so we do not lower the frequency with the measurement system. And also for the dynamic and static displacement measurement, we have 2 separate systems based on laser technology. The table around the machine is not connected with the vibrating part, so we can place here some equipment, camera for example, or maybe a heating system. There is the possibility to use normal specimen known in fatigue testing, round specimen with a thread for the high load, but there is also the possibility to test flat specimen with a fixture that is working with wedges, or also a fixture for round specimen without the thread. And one can even test small components as long as they are stiff and small. At the Fraunhofer Institute at Dresden, they could even place a very small corrosion salt spray chamber on the vibrating part, on the bottom part, and without affecting the smooth running of the system. So now in the second part, I would talk about frequency effect, mainly about the temperature rising, which is related then to the high loading frequency. It's the frequency effects can be divided in 2 sections. One is the intrinsic influence, which are really related to the strain rate, to the plastic deformation. And there is also an environmental effect, which is simplified, are all effects that are related to time. They are time depending for the formation of a new surface. It's not easy to separate these effects. Mr. Schneider from Technical University of Darmstadt could do it by using a 20 kilohertz ultrasonic testing system and a huge 400 hertz hydraulic testing system, and doing testing in inert atmosphere and normal environment in air. He found that on a martensitic steel in medium hard condition, he found a very big influence on fatigue life. The influence is bigger on the left side of the Wöhler curve than on the durability side. And a similar effect he could find when testing the same material in inert atmosphere. So he could conclude then, especially that on the same material in very hard condition, he could not find a frequency effect. That this is really must be related to the strain rate. One had also to have in mind that the strain rate is not constant during testing. It's a sinus shape, and so it is not so easy to really to understand and to make the right conclusion. And for an aluminium alloy that he tested, he could found almost no effects when testing in inert atmosphere. So he could conclude, but a big effect in air. So he could conclude that this must be related to environmental effects. So now the question is maybe what can we do? What can we see on 1000 hertz compared to lower frequencies? This, of course, I cannot tell you, but we have planned together with the University of Osnabrück an investigation of testing of this steel material to get a first idea. but I can show you a very interesting investigation that Mr. Pessoa could do at the Fraunhofer Institute in Dresden. He used two resonance fatigue testing machine, one running in 1000 hertz, our new system, and a traditional resonance testing machine running on 100 hertz, and he could found a very interesting effect that testing this austenitic steel, he could find that less strain-induced martensite is formed on higher testing frequency, leading then to a smaller crack growth rate. So by having two similar systems, also quite small effects can be detected. Now to the temperature, probably the most relevant effect. Yes, thank you. The most relevant effect. So we have, when deforming a solid material, there's also always a damping effect, a damping present, and in case of fatigue, there is also microscopic plastic deformation present, which is also the damping finally, and is finally completely generated to heat. So the generated heat is constant for one cycle, and as a result, the generated heat per time is proportional to the loading frequency. The temperature then, of course, depends then also of the heat losses. The heat flows to the fixture and to the air, which is also material depends also on the material, of course. So by using compressed air, it's a very efficient method to cool down the specimen in case it is needed because of heating up. Now I can show you some examples that we could test at Rummel with specimens that have been provided by interested laboratories. The first is a 9% chromium steel, a material with some damping, which is known for that it has some damping. And we conducted load increasing tests. The red dots is the load, the blue is the frequency, and the green is the temperature. By switching off the compressed air, we could illustrate how efficient the cooling is with the compressed air. So at this test run with 1024 hertz, at a load then of 333 megapascal, the temperature was 26, respective 54 degree without any cooling. So the cooling is very efficient. Another example with higher damping material, here the test run only with compressed air nodular iron. The behavior is similar as expected. And an example of a specimen with very high damping, a ferritic steel, here we see that the temperature is still increasing, being on the same load. So here some softening takes place. And this is probably here the application of doing testing on 1000 hertz is probably not the right way. And finally, an example of a material that has little damping. With this titanium alloy, it was possible to do testing without any cooling. So with that, I come to the end of my presentation. So to summarize it, the GigaForte is a very efficient tool for doing testing in the high cycle and very high cycle regime. And we can use common specimen types addressing the scatter of a production method, for example, of a material. And usually it's possible to test without interruption. Continuous testing is possible. So the heating up is moderate or very low normally. So, and I believe that with this the use of these testing machines, we can get further enhance the confidence on fatigue data, especially in the very high cycle fatigue range. Thank you for